wait till this starts. Okay, so that we can have enough time to do our makeup today, let me go ahead and start because we're going to lecture a little bit first. So pass that out in a few minutes. I think more people will show up. So we're going to start and do a little bit of lecture and then stop here maybe about 10 after 9. So remind me so that we'll have time to do the makeup for those people who want to do the makeup. And then as you're leaving, turn in your homework number 3. Just put it right here. And I'm going to, I'll post the answers immediately after class. So I've got the answer key so for that homework 3. So I'll post those on the Blackboard page just almost as soon as I get back to my office. So y'all have that available if you want to see the answers. And then be working on homework 4. So we should be ready to do homework 4 after today, finally, okay, if I can get through these examples. So, but we'll get through enough of them that you can, I think, do the homework number 4. All right, so let's go ahead and start. Last time we were talking about partitions, and so in a partition, it has kind of the terminology here is not the terminology, but the notation is a little bit complex here because partitions are generalizations of combinations. Remember, a combination is just a fancy way, a combinatorics way of saying a subset of a set, right? And we're often interested in counting how many ways we can, take a subset of a particular size out of a set. But remember, when you take a subset out of a set by just implicitly, right, you're leaving some elements in the set. That's the complement of the subset, right? So you're really partitioning the set into 2 pieces, right? The subset that you choose, the combination that you choose, and then its complement, okay? And so we're going to generalize that idea for partitions. In a partition, we're going to break the set up into a collection of subsets whose union is the whole set. But it's not just 2, okay? So when you build a combination, you get the combination and its complement. That's 2 partitions. But in general, you can have, multiple partitions, right? Okay? Again, as long as the union of the partitions are all subsets of the big set, right? The universal set. And the union of all the partitions has to be the whole set. You can't leave anything out of one of the partitions. Now, what's implicitly understood, though, and this is important, so you have to watch this in the problems, when we're counting partitions, because I'm going to give you a theorem for counting partitions, but it's very similar to the theorem for counting combinations. When you're counting partitions, you are assuming that you can identify the different objects in the set, right? So they are all distinct, but also the partitions are distinct. So you can also distinguish between the individual partitions as well. Right? So that's important because otherwise this theorem will not apply. So I think we'll see some examples here where we appear to be building partitions, but we can't either distinguish the objects in the set or we can't distinguish between the partitions, and then this theorem does not apply, and then we have to start improvising in order to count. All right, so here's what the theorem says. So you've got a set, right? And you're going to build the set of, this is the set of all possible partitions of particular size from that set. So what these subscripted R mean values are that's the number of elements you put into each partition. Okay, so you're going to break the big set into K subsets here because there's K of these R values. And the first partition is going to have R1 elements in it. The second partition is going to have R2 elements in it, up to the last partition is going to have RK elements in it, right? So you see that? Kayla, you're looking confused, right? Okay.
Does that say multinomial?
Multinomial coefficient, right? Okay. So here's how you count then the number of those partitions. It's a very simple formula, okay? You just take the size of the set, right, factorial, and then divide it by the product of the factorials of the sizes of each of the partitions, okay? So this is really the combination formula. This is really the same as the combination formula. Remember, in the combination formula, you take the size of the set factorial, and then you divide it by the size of the combination, and then factorial, and then the size of the complement factorial, right? Okay, because in a combination you have two partitions, the set and its complement. Well, in general, you may have multiple partitions. Okay, you still divide by the factorial of each of the sizes of the partitions. This quantity is there's a shorthand for that. It's not much of a shorthand actually, but here's the shorthand for this this quantity. Okay, it looks like the combination notation, right? Okay, but remember, a combination is called a binomial coefficient. This is referred to as a multinomial coefficient. All right. Okay, so all right, so that's all kind of a big jumble there, right? Until we actually apply it. But once you see it applied once, then it's very easy to understand what's going on. So let's look at a very simple application. Again, we're going back to our class, and we're breaking it up into teams. But this time, instead of just choosing one team of size 5, we're going to break the class up into 4 teams of size 5, right? Okay, so everyone will be on a team. So that's the question. How many ways can we divide the class into a red team, a blue team, a green team, and a purple team? So notice there's 4 teams there, and you can distinguish between the 4 teams, right? Because they're all given names. They all have these color names, right? So you can distinguish between the 4 teams, and you can also distinguish between the of course, the people in the class, right? Okay, so you're breaking distinct objects into distinct partitions, all right? And so how many ways can we do that? That is merely that's merely a partition, right? Okay, because I've got the 20 elements of the class, right? The 20 persons in the class, and I'm breaking them up into 4 partitions. Each one of the teams is a partition, okay? And we know the sizes of the partitions. In this case, they're all going to be 5. They don't all have to be the same size, but in this instance, they're all the partitions have the same size. So the number of ways of doing this is very easy, right? Okay, it's just going to be 20, choose 5, 5, 5, and 5, right? Okay, it's just that multinomial coefficient, which is going to be 20 factorial over 5 factorial, 5 factorial, 5 factorial, 5 factorial, right? So notice that, again, the numbers in the denominator, right, they have to add up to the number in the numerator. By the miracle of arithmetic, okay, this is guaranteed to reduce to an integer, okay? So at first you're thinking, wow, there's no reason why that should be a whole number, right? Okay, lots of factors in the numerator, lots of factors in the denominator, but it turns out they all cancel, and you will end up guaranteed to have an integer. Makes sense, right? Because the answer to this question has to be an integer, right? Okay, so, but indeed, that multinomial coefficient will always be an integer. We're not going to compute it, okay? That would take us a little while to actually calculate it. Your calculator, your scientific calculator will probably compute combinations for you. There's probably a key for combinations, but I doubt if there's a key for, unless it's a fancier programmable calculator. There's probably not a key for just partitions in general, multinomial coefficients. All right, so it takes a little while to simplify this, so I'm not going to simplify it. Does that make sense now? What's happening there? Okay. So if you were just breaking, if you were just choosing, which we did last time, right? If you're just choosing a team of size 5 from the class, right? Just one team of size 5, then you would have 20 factorial, 5 factorial, 15 factorial, right? Okay, because when you choose a team of size 5, you are implicitly then leaving 15 in another set, right? Okay, the complement. So that is an effective partition, right? The team and the non-team members, okay, are the two partitions there, all right? Here our partitions are just a little bit more explicit. They're these 4-color teams, all right? Let's see now how we can apply this same principle now of partition. This is a very powerful counting principle, okay? So, because it's really a generalization of combinations, all right? So you could really replace the combination theorem with just this theorem, okay? Well, this actually is, okay, the first part here is not a combination, all right, okay? So how many ways can we rearrange the letters in the word mud pie, okay? All right, so that certainly does not even appear to be a combination, right? That looks like a what? So what sort of model would we use to answer this question? Yeah, that's permutation, right? Because it's talking about arrangements, right? So that's almost certainly a permutation, which it is, all right? Notice all the letters here are distinct. Did I do that right? Yeah, those are all distinct letters, right? So you have 6 distinct objects there, and you're just arranging them. So that is clearly permutation, right? So the answer to this is simply what? 6 factorial, right? Okay, that's the number of permutations of 6 objects, right? Is 6 factorial. That would be in our notation, right? P66, right? Which is 6 factorial. Okay. All right. So that was the easy preparation for the next question, because you see the difference here, right? How many ways can we rearrange the letters in the word Mississippi? All right. So that again appears to be initially that's a permutation type question, right? Because we're rearranging objects, correct? But it's just not going to be a straightforward permutation like in the part A, right? Because of course, obviously, what's the issue here? Yeah, we have duplicates, right? Okay, so you can it doesn't make any difference, right, if you rearrange the S's, because they just look like S's, right? Okay, so you cannot distinguish the S's from one another. So you don't have distinct objects here. How many letters do we have, by the way? I didn't count this up. So this is what, 1, 2, 3, 4, 5, 6, 9, 10, 11. Okay, yeah, so the answer is not 11 factorial, right? Okay, because the objects are not distinct. All right, so we're going to think of this in a little bit different way. All right, okay. Instead of thinking of this is a permutation problem, I'm going to think of it as a partition problem, all right? And what I'm going to be partitioning, and so here you see this deep connection here between partitions and permutations. What I'm going to think of partitioning are not the letters, all right? I'm going to think of partitioning the positions in the arrangement, all right? So this is a typical exercise, right, in combinatorics. A particular skill in combinatorics, right, is learning to think a little bit sometimes differently, right, about what you're actually arranging or what you're actually partitioning. All right. So we're going to think of the positions in the final arrangement as being a set of things, all right, that we're going to partition into the letters. All right. So you're almost always thinking of this as, because of the way the question is at, is somehow arranging the letters into the positions. But we're going to think of it backwards. We're going to partition the positions into the letters. Let me show you what I mean. Okay. All right. So how many positions did I have there? Right. Okay. So there are my positions, right? 1, 2, 3, right, up to 11. Okay. So I guess I can represent that set of positions, right, by this integer segment, right? Okay. And correct. And now I'm going to think of my partitions, okay, as being labeled with letters. All right. So here are my here are going to be my subsets here, right? And how many distinct letters do I have there? So let's say I have some I's, right, and some S's and some P's, and that one M. Is that it? Oh, that's nice. Okay. So I'm going to break this set, this integer segment, which represents my positions, into a partition, right? But I'm going to label or distinguish the partitions by the letters. So let's see, what are the distinct letters there, right? There's M, I, S, and P, right? So let's build one of these. Let's build one of these partitions. Okay. Now, when I build a partition, though, I also have to tell you. Remember, this is a key thing to partitions. I have to tell you how many elements are going to go into each of my partitions, right? Okay. So remember, the partitions have to be distinguishable. right? Okay. Here I'm distinguishing them by these letter names, okay? So I could number them, but I'm going to distinguish them by the letter names. And remember, the objects you're partitioning have to be distinguishable, right? Okay. So that's my set of positions. All right. Now I also have to tell you how many objects are going to go into each one of these partitions, but you can guess this, Sean. How many objects are going to go into M? One, right? Okay, because why? There's one M. That's right. Okay, so my R sub 1 here, using the notation from the theorem, the number of elements in my first partition is going to be 1. What about R sub 2, Sean? Obviously here, can we count that? Is that 4? Right. What about R sub 3? Is that also 4? And 2. All right. So R sub 4 there is 2. All right. Well, let's actually make one of these partitions. Right. So Kaylee, just start throwing elements from this set right into the partitions. Right. But you can do it however you like. So remember, you got to pick one thing out of here and put it here, 4 things out of here and put them here, 4 things out of here and put them here, and then 2 things out of here and put them here. But you can't duplicate things, right? Because the union of this has to be the original set, right? Okay. So just 1. Okay. Well, all right. That's getting a little bit boring. So let's get wild with me here. What about 11 here? All right. Okay. What else? So you got to have 4 things here.
7, 2, 9, 4.
4. All right. That's great. Now you got to have 4 things here. Now you got to remember what you haven't used, right? So 5. Okay. 3, 8, 10. All right. I'm going to squeeze the 10 in there. And now 2 here. What's left?
1.
Is it 6? There we go. All right. All right. Perfect. All right. So Kayla, you got that down. All right. That's a partition, right? Okay. And do we know how many of those partitions are? You picked one of them. That was hard enough to do, but there's a lot of them, right? Okay. So good thing we don't have to list them all. Okay. And by the way, now, it's really important that, again, you can distinguish between the partitions. So if you could not distinguish between the partitions, notice that that would make it very difficult, right, to distinguish the fact that we have 7, 2, 9, 4 here, right, and 5, 3, 8, 10 here, because these 2 sets have the same number of elements in them, right, okay? So if you couldn't distinguish between the partitions, if you switch these 2 partitions, you wouldn't know that, right? Okay, but fortunately we can distinguish between the partitions, right? So so now here's the second part, right? I'm claiming that that the number of that this set of partitions, which I really don't have a notation for, is but the set of partitions here is a model for this the ways of arranging these letters. Okay, so can you take this partition and tell me what arrangement of letters this corresponds to? All right. So it's got to be arrangement of the letters. So I'm going to fill up 11 positions, right? How many have I done there? 1, 2, 3, 4, 5. Is that it? 11? Okay. All right. So what arrangement does this partition match? It's not this one. Okay. So what'd you say? P, I, S, I, S, E, P, another P, P here. I know M is down here, right? What? I, S, S. There we go. Can y'all read that? No. All right. So, but there it is. Okay. So there's the arrangement. All right. So that's it. See? Okay. So how did the partition correspond to the arrangement? Well, you just simply looked here at the positions that were in this partition, right? And you're going to put M in those positions, right? You looked at the that the positions that were in this partition, right, you're going to put I in those positions, correct, right, okay, and so on and so forth, okay. So it's very easy to work from a partition back to an arrangement of letters, or vice versa. If I gave you an arrangement of the letters like Mississippi, you could tell me the partition, couldn't you, right, okay, that corresponds to that, right, okay. So in M it would be 1, that's why I was trying to steer you away from that, right. What would be in the I partition? 2, what's that? 5, oh, I don't know. Okay, 11 would be in there, and whatever that number is. What is that, 7 or 8 or something? Yeah, okay, right, okay. So you see there's a one-to-one correspondence between the partitions and the arrangement of the letters. So if we can count the partitions, then we can count the arrangements of the letters. But we know how to count the partitions, right, because that's what the theorem tells us. Yeah.
So, n is 11, right?
What now?
From the theorem, n is 11.
N is 11, right, okay, because you're breaking 11 objects, right? That's the set you're partitioning into 4 partitions, and again, R1 is this, R2 is this, R3 is this, and R4 is this. So, so the answer to our question is pretty easy, right? It's 11 factorial, right, over, what is it, 1 factorial, that's kind of boring, 4 factorial, 4 factorial, 2 factorial, there you go. Does that reduce to an integer, Bradley? Is that an integer? Well, it is, okay, but do we have any idea what integer that is? All right. Someone can calculate that while we're doing the next example, which is very similar, okay? All right, because I'm just curious what that number is. All right. Actually, I'm curious if it really turns out to be an integer, okay? All right, so in some of the past lectures, I had included some questions. I had included some questions in the margins that were a little bit more complicated versions of the original question that I said we can't answer this now, but we'll be able to answer it in the future. Here's one of those margin note questions. Okay, I think before we were arranging. We were trying to arrange the digits 3, 8, and 3 1s, right? Okay, and we figured out how to do that before. But then I said it's a much harder question if we had 3 1s, 3 3s, and 4 8s to arrange into a number, right? Okay, but now you know the answer to the question because we're going to answer it just exactly like this, right? So if you build an integer, a 10-digit integer out of these 10 digits, then and I asked how many such integers can you build, right? Okay, then how are you going to think of that? Yeah, that's right. So when you build one of these numbers, right, you actually have to arrange these what? 10 positions, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Okay. So you have to arrange those digits into the 10 positions, correct? Yeah. Right? And so what we're really asking there is how many ways can we arrange these 10 digits, right, in these 10 positions? Okay. That's not just permutation problem because we've got these repeated digits, correct, right? So instead we're going to think of it as partitioning the 10 positions in the final number, right, into 3 partitions where the number of each element where the partitions are labeled by the digits and the number of elements in each partition is determined by the number of that digit, right? Okay. So we're breaking what into what? Again, I don't have a notation for this, which is unfortunate. So what set am I partitioning? Yeah, the positions. That's the easy set. What set is that? 10, right? Okay. That's the integer segment 10, right? Okay, yeah. And I'm partitioning that in my really crude diagram here, right? I'm partitioning that into how many partitions? 3. That's right. Into 3 partitions, right? The partition that I'm going to label as 1, the partition I'm going to label as 3, and the partition I'm going to label as 8, right? Okay. And how many things can go into this first partition? 3, right? So R1 in our counting theorem is 3. R2 is that also 3? And then our 3 is 4? Yeah, because we have 4 8s, right? Okay. So I just take those, somehow break them up into these 3 partitions, and then I could look at what's in each partition and build my 10-digit number, right, from examining the partitions. Or vice versa, if I gave you a 10-digit number, you could tell me, oh, that corresponds to this particular partition of the 10 digits, right? So the answer to my question here is really straightforward. It's just what? 10 factorial, right, over 3 factorial, 3 factorial, 4 factorial, correct. Nice. Let me split these 2 things up, because those are different problems. Did anybody calculate that? What now? 34,650. All right, so you can ask that if you're at a party at spring break, right? All right, here's another one of the margin questions that we asked, okay? And this was way back early in the semester, all right? So, so remember, a complete traversal of a chessboard is, that's a defined term, complete traversal. And so what that means is you're going to start in the top left-hand corner, and you're going to move, right, into adjacent squares, correct? And you're going to travel down to the bottom right-hand corner. But you have to do that in a particular way. You can only move to the right and down, okay? So you cannot back up, in other words, right? You cannot go ever to the left, or you cannot go backwards. You cannot go up, all right? So so this is an example of a complete traversal of the chessboard, right? Okay, because I'm always moving to the right and down, right? Okay, I don't go backwards. But there are lots of those, right? Okay, because I could go like this, right? That would be another complete traversal. Or I could go like this, right? Okay, so this is one out of lots of complete traversals, okay? And so that's what I want to do. I want to count in my usual way, right? I want to count the number of complete traversals, okay? Any suggestions here on how to proceed? Can you, here's the thing to think about. Can you think of so that's a particular complete traversal, right? So but I drew a diagram of that. If I didn't draw a diagram of that, if I was just describing that traversal to you, but without a picture of the chessboard, how could I describe it to you so that you could reproduce the diagram? What do I need to tell you so that you will understand what this traversal is, okay? And you could redraw it. Kaylee's dying to answer here. All right, so go ahead.
The number of rights and downs, like separately, like.
Well, I think I know the number of rights, though, okay? Because in a traversal, in a complete traversal, how many moves to the right do there have to be, ultimately? Is it 8? No, 7, right? Okay. Yeah, there have to be 7 moves to the right. And how many moves down do you have? 7, right? Okay. So you have to have 7 moves to the right. But that's just, you have to, right? Okay, to get from left to right, you have to have 7 moves to the right. And to get from the top to the bottom, you have to move 7 moves down, okay? But, so we know, Kaylee, that there's 7 and 7 of these things, right? Okay. But what is it that we don't know? So what changes traversal? The order, right, okay, yeah, it's the order, right, okay. We don't know the arrangement of the right moves and the down moves in the traversal, okay, right? So how would you, so if you were trying to describe someone this complete traversal, right, okay, but again, without drawing the diagram, you could describe it by the number of, by the arrangement of the, or the order of the right moves and the down moves, correct? Right? Okay. So what would that be? Here. Well, how did you start? What did you do first in this traversal? You moved right, right? Okay, and then you did what? Right. Again, correct, right? And then what did you do? Down twice, is that right? And then what? Right, and then what? Down twice again, or, oh, 3 times, right? Okay, and then what? Right, down, 3 rights, and 1 down. There you go, right? Okay, is that 7 Ds and 7 Rs, right? Okay.
One of those is a P.
What?
One of those is a P.
A P for what?
No, no, you wrote a P.
Where did I write a P? Oh, was I trying to write an R? Okay, all right. All right. Okay, I thought you had a joke there. One's a P because. All right. All right. So we do have a problem like that coming up, though, kind of. All right. So so what have we? So there's kind of our that would be kind of our verbal description, right, of a complete traversal. I guess you could write it out in words, but this is almost as good, right? So there's our symbolic description of a complete traversal, right? Not a diagram, but you could reproduce the diagram easily, right? Okay, from this symbolic description, okay? But how do you get other complete traversals then? You mix up the order. In other words, you just rearrange what here? The R's and the D's. So what's my model for the set of complete traversals? Let's call that S. So this is the set of complete traversals. So what's my initial model for that, Dalton? So what's my beginning model here? I'm saying the set of complete traversals corresponds to what? Yeah, the set of something with this, not combinations. Arrangements, maybe. Okay, there we go. That's all right. Or I guess you could say permutations, because permutation is an arrangement, right? So, but I'm going to say arrangement just to keep us away from the term permutation. All right. So, set of arrangements of 7 R's, right, and 7 D's. Ah, there we go, right? Okay. So 7 R's and 7 D's. So there's our initial set model, right? Okay. We know these two, just by the description I gave, we know these two sets correspond to each other. But now I need a model for M. But what's my model for M? So I'll call this M prime here. Set of, how do we answer that now? I don't think I even need to write set of. What? Oh, no, I do, right? So it's what?
14 placements?
Yeah, no. So we have the set of arrangements, right, of these, right? So that looks like the previous 2 problems. So how do I model the arrangement of the 7 duplicate R's and the 7 duplicate D's? That's just like the Mississippi problem, right? Okay. Yeah, so you take integer segment 14, right? And then what do you do with that? You break it into what? R's and D's. And you're thinking of those R's and D's as? No, okay. Partition, right, okay, yeah. So you're going to take that set of positions, which is the integer segment 14, and you're going to partition that into how many partitions? 2, right, okay. One with what? How many things in it? 7. And the other with 7, right, okay. Oh, now, when you break a set into 2 partitions, that is called that's a particular type of partition, right? That's just a combination. That is a combination. Yeah, right. When you break a set into two partitions, right? That's just a combination. Okay? Because a combination is just a subset and its complement. Well, that's what we'll have here, right? We'll have the positions that are going into R, and then the complement of that will be the positions going into D. Correct? Right? Okay. So actually, I have a name for a set of combinations, right? So I don't need to spell this out. What's my notation for set of combinations? What are we breaking up? 14. Choose what? There we go. Right. Okay. So, oh, good. I don't have to write that out in words. I actually have a notation for that particular set. And now I know how big that is, right? So I know that S now. So M prime and M are models for one another, right? Okay. So working backwards, I know that the cardinality of S is the same as the cardinality of M prime, but I know what this is, right? What's this? 14 factorial over what? 7 factorial, 7 factorial, right? Okay. Okay. Yay. So there's another one where we had to be a little bit indirect, right? Okay. Because I had to first think of S as being a set of arrangements of these letters, and then I had to think, oh, how am I going to model the set of arrangements of these letters? Oh, that's really just a partition, or in this case, a combination, right? Okay. All right. I want to show you quickly here. I'm not going to be able. We're not going to have time to talk about finite probability, but I think there's a few homeworks problems like this. I think you'll understand this finite probability pretty easily. Finite probability is really important in combinatorics, or actually, I should say combinatorics is really important to finite probabilities, okay? This is how really counting principles were first developed in the Enlightenment, is to help understand probabilities. And they were probabilities for games of chance, because games of chance, people like to gamble, right, on games of chance. And so to understand gambling odds, people had to understand probabilities associated with games of chance. And those probabilities, combinatorics is very useful for helping us understand those probabilities. So this is where basic counting principles were first developed, is during the Enlightenment, in the 1600s and the 1700s. It's also the time calculus was developed, and lots of other branches of science and mathematics started at that time, and that's why it's called the Enlightenment. And because the wealthy classes and the royal classes liked to gamble, okay, they had money, so they liked to gamble, and so of course they wanted to win, right? So they were interested in understanding these probabilities, and so that's how there was this motivation, right, to understand basic counting principles. Okay, so I'm going to ask you a probability question, but we're not going to answer the probability question. I just want to get started here on this question. So suppose that you're going to write down solutions to this equation, but you want your solutions to just be integer solutions. So you want x1, x2, x3. You got to write a solution to the equation. So that means you got to tell me what x1 is, what x2 is, and what x3 is. But I want those to only be integers. And in fact, I want them to be non-negative integers, okay? So only non-negative integer. My question is, how many solutions then are there to this equation, okay? It's easy to pick out solutions, so there are lots of them. Sean, can you tell me just a solution to this equation? Obvious one?
Yeah, 5 plus 11 plus 4.
Okay, that wasn't the one I was thinking of, but that one's obvious too, right? Yeah, 5 plus 11 plus 4. So x1 is 5, x2 is 11, x3 is 4. I was thinking you were going to say x1 is 20, x2 is 0, x3 is 0, right?
It's trying to be interesting for you.
Okay, all right. All right, so it's easy to generate solutions, right? We just want to know how many solutions there are, okay, to this equation. Non-negative integer solutions, okay? So we're simplifying it somewhat. And actually then this question has to do with, well, how many solutions do we have where all of the variables are at least 2? But let's not worry about that. Just non-negative integer solutions, okay? So that's what we're trying to count, is the set of solutions Let me show you now how we're going to model the set of solutions, though. Okay, so there's indirection here. You have the set of solutions you're trying to count. I'm going to show you a model for the set of solutions, and then we're going to have to write down a model for the model. Okay, but once you see the model for the set of solutions, you'll know immediately what the model is for counting that model. Okay, all right. So here's what I'm going to do. I'm going to write down this. What'd you say, Sean? Do you remember what you were? 11 plus 5 plus 4?
Yeah.
So I'm going to write down, just like we sort of did last time, a sequence of zeros and slashes. Okay? How does that correspond to Sean's solution? Yeah, the number of circles is an integer, right? And notice it happens to add up to what? It all adds up to 20, right? But this first sequence of zeros, right, is my that corresponds to my value for x1. This second set of zeros corresponds to my value for x2, and that third set of zeros corresponds to my value for x3, right? Okay. So if I gave you any solution, there, Eric, if I gave you the solution I was talking about, which was 20, 0, 0, that would look like this, okay, where you have 20 zeros to start with, all right, because that sequence of zeros and ones would mean 20 is x1. How many zeros do I have between the slashes? None. So x2 would be 0. How many zeros do I have after the last slash? None. So x3 would be 0. Got that right? Okay. So any arrangement of the zeros and slashes will give me a solution to this, right? Okay. Or vice versa, any solution I can convert to arrangement of the zeros and the slashes. Now, do you know how to count the number of arrangements of the zeros and the slashes now? That looks a lot like counting the number of ways of arranging the R's and the D's, right? Okay, or it looks a lot like the number of ways of counting the letters in the letters in Mississippi, right? Okay, so all of those problems are really all these counting problems are really the same problem. They're all just a type of, what's the model that we use here? Begins with a P. What? It's a partition, right? Yeah, these are all partition problems, right? Okay. In this case, what's the answer really quickly? So we're going to take what? How many positions? 22, right? And we're going to partition them into what? Zeros and slashes, right? How many slashes? Because that's easy, small number. What? 2, right? Okay. And then the rest of them have to be in what? Zeros, right? So you get 22. So I can use a binomial coefficient in this case, just a binomial coefficient. So you get 22 factorial over 2 factorial, 20 factorial. There it is, okay? There's the number of non-negative solutions to that equation, okay? All right. All right, so we got to stop there. And